Remember, light is only one of the many types of electromagnetic radiation. Scientists have conducted similar sorts of experiments with the other types of electromagnetic radiation and have established that they too display the same wave properties as light. In other words, all electromagnetic radiation has the properties of transverse waves and can be thought of as a combination of two transverse waves that act at 90 degrees to each other. Now, let's find out why this form of energy is called electromagnetic radiation. You have previously learned that there is a relationship between magnetic and electric fields. Remember, when a charge moves through a conductor, a magnetic field forms around the conductor at 90 degrees to the direction of movement of the charge. So a moving charge produces a magnetic field, and the converse is true too. When we move a magnet in and out of a coil of wire, we can see that a current is induced in the coil. We can see this as a changing reading on the galvanometer. This changing reading indicates a changing electric field. So, a changing magnetic field creates an electric field that also changes in magnitude. Keep the relationship between a changing magnetic field and a changing electric field in mind as we now look at a model of an electromagnetic wave. A model that was first stated by a 19th century Scottish physicist by the name of James Clerk Maxwell. Maxwell said that when a charged particle moves from rest to a higher level of energy and back down again, in other words, when it oscillates, a changing magnetic field forms around the charged particle. But this changing magnetic field induces a changing electric field at right angles to it. And this changing electric field, in turn, induces a changing magnetic field at right angles to it, and so on. In other words, each field generates the other, and a continuous electromagnetic wave will be produced as long as charges oscillate, that is, moving up and down. As the charged particle moves, the magnetic field, shown by the blue line, will increase to its maximum strength, represented by the crest of the wave, then decrease back to zero. Now it will move in the opposite direction and increase to its maximum strength in this direction, represented by the trough of the wave. And then, once again, it returns to zero. But as the magnetic field changes, so it produces an electric field at 90 degrees to the magnetic field. The electric field, which is represented by the red line, will reach its maximum and minimum strengths at the same time as the magnetic field. This means that the two fields are in phase with each other. We can clearly see that an electromagnetic wave consists of two transverse waves, which are perpendicular to each other. Note the following characteristics. The electric field is in the same plane as the oscillating charge, shown here in the vertical plane. The magnetic field is always perpendicular to the electric field, so here it is in the horizontal plane. Notice too that the frequency of vibration of the charge is the same as the frequency of the wave produced. When high-energy charged particles accelerate rapidly, high-frequency electromagnetic waves are produced. These electromagnetic waves have a very short wavelength. But when the frequency of the vibrating charge is lower, the frequency of the wave is also lower, but the wavelength is longer. The charged particles in the sun oscillate with different frequencies, and so they produce a range of electromagnetic waves, all with different frequencies and wavelengths. This range of electromagnetic waves is called the electromagnetic spectrum. All the waves of the spectrum travel through space or in a vacuum at the same velocity, 3 × 10⁸ meters per second. The symbol for the velocity of an electromagnetic wave is c. Now remember that the velocity of any wave is related to its frequency and wavelength by the equation v = f × lambda. Now I want you to use this relationship to complete your calculation for today's task. Calculate the wavelength of a beam of red laser light with a frequency of 4,74 × 10⁻⁴ Hertz. In our next lesson, we will explore the electromagnetic spectrum in more detail. Bye for now.